Good afternoon, everyone. My name is Dongyin, and I'm from the University of Pennsylvania. I'm really excited today to tell you how we can track blink dynamics and mental states using glasses. This is a joint work with my colleagues Xin, Ahhyun, Zhao, Lama, Insup, and my advisor Mingmin. So I wanted to start with the story of my friend Sarah. Sarah is a poor graduate student, and last month she was trying to meet her conference deadline. Even though it was already midnight and she had been working for 14 hours straight, with her advisor expecting the first draft in the morning, she told herself, maybe I should work for 1 more hour. Her smartwatch is tracking everything, her heart rate, her step count, and even her sleep quality from last night. However, it's completely missing the most telling sign of her exhaustion. Her blinks. Sarah's blinks are changing. She felt her eyelids are getting heavier, and she's blinking less. Each of her blink is not fully closed anymore. Yet, none of these important signals are for mental states being heard. And this is not just something specific to Sarah. It actually happens to all of us. It's a common phenomenon we experience throughout our daily life. Many prior studies have shown that blinks as a proven marker for mental and eye health. When we're feeling drowsy, our eyes close longer and they reopen slower. This explains why we are feeling our eyelids are heavier when we are drowsy. And with heavier workload, we see blink inhibition, which means that we blink less and each blink becomes faster. And finally, for health conditions like dry eye disease, patients have more partial blink, where their eyes don't fully close. But in order to read these markers, we need to take a closer look at blinks. Usually people think of blinks as single events, but if we examine them in slow motion cameras, we can see it's more than that. It's actually a continuous process where the eye openness changes smoothly. It contains 4 phases: closing, closed, reopening, and open. And the minimum of the curve tells us whether it's a partial or full blink. And we call the timing of each of these phases the blink dynamics, and they tell us important information about mental and eye health. Unfortunately, for existing solutions, they are caught in the trade-off between the granularity and practicality. On the one side, we have clinical systems, for example, the EOGs and also the high-speed cameras. They can track blink dynamics down to milliseconds, but that comes at a cost. They're bulky, expensive, and limited in lab environments. And on the other hand, we have the mobile systems. For them, we can use them throughout the day, but they only count the number of blinks. They completely miss the dynamics, which are important for us to understand what's happening in our minds. And here comes our system Blinkwise. It combines the best of both worlds, the high-grained details, as in clinical systems, and also the practicality of wearable devices. Blinkwise is designed as a tiny lightweight add-on. You can clip it onto any regular pair of glasses, and then forget it's even there. It's that comfortable and unobtrusive. And under the scenes, it has ultra-low power consumption, which means Blinkwise can run an entire day with a single charge while processing everything locally. This avoids power-hungry communication while maintaining privacy and mobility. Most importantly, Blinkwise captures eye openness at a rate of 900 frames per second. That's a millisecond precision. Whether it's a partial blink, or a quick double blink, or even a long blink, Blinkwise doesn't just detect it, it captures them all. So Blinkwise sounds great in theory, but the key challenge lies in the severe resource constraints on these edge devices. First, memory. Typical microcontrollers only have a few kilobytes of memory. That's even smaller than a selfie on your phone. However, our machine learning algorithm require megabytes to run. Second is the power. We want all-day tracking without draining the battery or interfering with any task that's also running on smart glasses. Finally, is the computation. Working at 900 frames per second, Blinkwise only have just over 1 millisecond to complete all the processing on average. So in order to overcome these challenges, Blinkwise provides the solution along 2 axes. Miss one. So how can we actually run those sophisticated machine learning under these severe constraints? So our solution is along 2 axes. First, we have efficient sensing, which means we use radio frequency signals to sense the eye openness. The second axis is efficient computing. We have to redesign the machine learning pipeline for running for streaming data on tiny devices. And let's look at the first axis. For efficient sensing, we began with the question, what's the minimal signal that can still capture the full dynamics of a blink? The typical solution is to use an high-speed camera, but the frame of an HD video contains nearly 1 million pixels, and only less than 2% of them cover the eye. The other pixels are just irrelevant information. If we can use RF signals to detect blinks, we will only require 128 ADC samples. That's over 3,000 times smaller in comparison with a video frame. If you can make this work, we can unlock massive saving on both the data sets and model complexity by using this information asymmetry across modalities. So the next question becomes how we can actually use RF signals to detect blink dynamics. The key insight lies in the eyeball and eyelids reflect the signals differently. The eyeball is moist, smooth, and more reflective, while the eyelid is drier, rougher, and more diffusive. During the blink, eyelid covers and uncovers the eyeball, which creates a consistent material change on the eye surface. From the reader sensor's perspective, we can see a specific pattern in the reflection. And here I'm showing consecutive 5 blinks. We can see there is a consistent temporal structure where we can learn to recognize. And since both vision and RF modality can observe the openness, we can transfer this knowledge from the rich yet redundant vision modality to the more efficient RF modality. We employ a powerful vision model to process the frame and predict the openness. And those predictions will be used to supervise an efficient RF model, mimicking the behavior of the vision model's output. This allowed us to achieve a similar performance with less than 4% of the parameters. So now we have this compact RF model that can predict eye openness, but it is still too big and too slow to run real time on tiny devices. Therefore, we need to go beyond efficient sensing, which leads to the second axis, efficient computing. As we mentioned, our compact RF model still require a lot of memories to run. So we began with this question. What's the reason for its high memory consumption? Therefore, we did a memory profiling of each individual layer of this network. We have some interesting observations. Most of the layers don't have really high memory consumption, but at the beginning, there's a huge spike, and it becomes the memory bottleneck, determines the total need. And this pattern is not just specific to our design model. It's actually common in all common CNN architectures like ResNet, MobileNet, and others. This is because the initial layers haven't really cut the data size a lot, but they are already expanding the number of features. If we can reduce this initial peak, we can save a lot. So we wonder if this is even possible. And the solution comes from understanding how CNNs naturally work. Here we're showing a very simple network with 2 layers cascaded together. Usually CNNs process everything in batches, which means it's great for powerful computers, but pretty bad for our streaming data. Why? Because we need huge memory to store the input and output all at the same time. And also we have to buffer all the data before we can start processing, which introduces high latency. The observation is that for each individual output, it doesn't require the entire input to compute. As in this example, the first output only determined by the values that are connected by this flow. This means that the CNNs are actually local. And also we can break down the input into smaller chunks and do all the computation. This helps us to reduce the memory and also the latency because we don't need to wait for everything to arrive. But if we do this naively, we would have to waste a lot of computation because CNN operations are also overlapping. Let's consider the second output. We can see that it shares a lot of computation in the middle layer with the first value, as shown in these dark squares. And in this example, if we directly apply this method, we would introduce a 67% of overhead. And our second part of this solution is a smart caching mechanism, help us to reduce overly computed results. Assume that these values are already cached. In order to get a second value, we don't need to compute everything. We only need to compute one new value in the middle layer. We update the cache and do the same for the third value. This creates a repetitive computation pattern as this graph shows. It looks like an RNN cell, right? But instead of doing matrix multiplication, we're doing customized CNN operation with smart caching. This is why we call our method modal recurrentization, because it converts convolutional networks into recurrent networks. This determines the exact same mass, exact same output, with much less memory, cost, and latency. So after applying this method, we can see that the original peak is being reduced by over 186 times, and the peak moves to a much smaller layer. So now our model can be fit in the microcontrollers, but we also need some extra memory for signal processing plus other overhead. That leads to the next question. Can we further reduce it? Using quantization seems to be a great option for here, but directly applying quantizations doesn't suit well with RF signals. Let's look at this example. We have the signal from two users, and their signals have different dynamic ranges. If we directly apply quantization, the signal of the user one loses important information, and we cannot decode their blink dynamics. And our solution is a smart normalization pipeline that is aware of the quantization effects. We build on max-min normalization because after this normalization, the signal distribution have a fixed upper bound. Therefore, it's used for quantization because the normalized range are consistent. But we're missing one thing. Those dynamic ranges are not static. They're changing throughout the day. Therefore, we need some sliding window technique to calculate some running statistics. But the problem with sliding window is that it again requires a very large memory because blinks can be really sparse. Some people can blink only 1 or 2 times within a minute. In order to capture at least 1 blink in the window, we need a very large one, and that requires a lot of memory. So the second part of our solution is a clever approximation of this exact sliding window method. We break down the window into smaller chunks, track the maximum inside each chunk. And once the chunk is finished, we update the exponential smoothing value as the running statistics. So after using this technique, we can see that both users are now fully utilizing the quantization space, and we're not wasting a single bit. So now we're good memory-wise, but the other two challenges, like computation and power, we still haven't solved it. If you run the machine learning algorithm for every single frame, we can easily exceed the computation budget, and also it quickly drains the battery. The question is, can we really save the computation and leave some resource for other tasks? Our observation is again from the sparsity. Because people, when they're awake, only 16% of the time is blinking. That means it's sparse and we don't have to run the algorithm for all the time. And that leads to our third solution, a 2-stage coarse-to-fine design. For a stream of data, we prepend a coarse filter algorithm, and it looks for potential patterns in the signal. Only when it thinks, hey, I think there might be a blink, does it trigger the more sophisticated network for processing. And this alone saves us 96% of computation. And how does everything look together? We fit our constraints. In memory, the model can now fit with just 135 kilobytes, and it is using only 64% of all the computation budget on average. Given the battery of a commercial smart glass, it can run for over 43 hours nonstop. We tested blink-wise with 20 subjects while we filled them to gather the ground truth blink dynamics. In total, we collected over 18,000 blinks. The result is pretty impressive. The blink-wise can achieve a piercing correlation of 0.98 with the ground truth from the camera, which means it's showing high alliance. Based on the curve, we can do simple blink detection with very high precision and recall. And what's more, we can further analyze the timing of each different phases. This is something impossible for existing mobile solutions. Now let's go back to my friend Sarah. We actually tracked the 8 people like Sarah throughout the day for 12 hours. At each hour, we collected their blink dynamics and also their drowsiness level. During lunch, we specifically provide some high-carb food to introduce food coma. And after that, we offer them coffee to help them refresh themselves. And this is what we discovered. In this figure, we are comparing the duration of the closed phase plus the reopening phase against the drowsiness measured. We see there is a very high correlation. And after lunch, we see that the closed phase and reopening phase, they're getting longer, and we also see a higher drowsiness level. That means the heavier eyelids are actually reflecting the drowsiness. And after coffee, we see that both phases are returning to the baseline with lower the drowsiness level. And something more remarkable is that these changes are adjusted within tens of milliseconds. That emphasizes that we really need a very high temporal resolution. We also do cognitive workload test by asking people to finish a visual search task. So the task asks those participants to identify an outlier circle that has a radius that is different from others. So I would like to pause a bit for everyone to look for it, and it's actually here. Did you find it? So in the blink pattern, we see some very obvious results. When the same person is under workload, we see that they blink less, and each blink is getting faster. And finally, we can also do health condition monitoring. So for dry eye disease, the blink-wise can detect a partial blink with an area under curve of 0.86. That could potentially help millions of people to check their ocular health continuously. So in summary, blink-wise is a mobile system that can enable 900 frames per second observation of blink dynamics on glass. We proposed an efficient sensing mechanism plus 3 efficient computing techniques to cut the memory need plus latency. And we showed 3 real-world applications of drowsiness monitoring, workload detection, and dry eye disease tracking. But here's the bigger picture. Smart glasses and AR headsets are becoming more popular. Imagine if all of these devices can have access to this hidden channel of information. Blinkwise opens up physiological signals that previous mobile systems have limited access to. We are moving toward variables that can understand what's happening in our minds better. And we have the codes dataset all available in our web page, so feel free to check out. And I'm open to take questions and discuss where this could go further. Thank you.
Thank you, Dongyin. Yeah, please.
Hi, my name is Jing Li from Michigan State University. First, congratulations, it's actually a very impressive full stack work. However, I do have more of a clarification rather than question. So you mentioned like 3 application examples. You use the Blinkwise. Are those application analyze themselves and also data transfer themselves part of the energy consumption you mentioned, like for your system? Or the energy, the efficiency in energy and sensing mainly just for detecting the blinking? Do you understand what I'm saying?
No, can you please repeat? Sorry.
Oh, I'm sorry. Okay. So you mentioned you have like a small model on the device, and also the energy consumption of that model is very efficient, can last very long. And then you also mentioned there are 3 downstream tasks, such as drowsiness or I don't know, like workload intensity, something kind of detection. Are those detection also happen the same time on board and consuming those energies, or just separate thing?
Yeah, thanks for the question. So the model itself is only for the curve prediction. It gives you the openness, the eye openness as a smooth curve. All the rest of the analysis is based on this curve. So those are 2 separate phases. You have to got the curve first, then do the analysis. So it's not in part of the job in the machine learning model.
Yeah. Thank you for the clarification. Just detecting the blinking is already impressive enough from my point of view. Thank you.
Sure, thank you.
Hi, I'm Taekyung Lee from KAIST. I was actually at yesterday's poster session, demo session, so it was very interesting to listen the details of your project. What I'm curious is that you once mentioned that you try to transform CNN-based models into like RNN-wise. But what I'm curious is that why do we even eventually needed a CNN-based model for blink detection? So what was your motivation, or what was your design choice for blink detection model?
Thanks for the question. I think I got a pretty similar question yesterday in the poster session as well. I think I think there is one hidden slide here. So we actually derived the exact relationship between the reflected signal with the eye openness. But as you can see here, it's pretty oh my God, it's not showing there. But anyway, we have those formulas, and the relationship is pretty nonlinear and very complex. So we tried to build some more signal processing-based methods, simpler methods, not machine learning involved, but those didn't work pretty well. And that's sort of the motivation why we're using convolution networks. And it sort of also depends because different users, they have different eye structures. So it's really hard to build a single model that suits everyone. So that's why we use the data-driven method. Yeah.
Okay, thank you.
Thank you.
Hi, I'm Bang Jie from National University of Singapore. So I really like your work and also the application scenarios that you have demonstrated. So I'm just wondering whether it is possible to differentiate between voluntary blink and non-voluntary blink. This is important because if you are able to differentiate it, then basically we are able to use blink as the gesture to control the AR/VR glasses. Yeah, thank you.
Thanks for the question. Actually, we did thought about these applications. And we originally also think how this can be used as an interface to communicate, for example, on AR headsets or something other stuff. But the thing is, we need to check existing literature to see if there are actual difference between like the pattern in voluntary blinks and involuntary blinks. But I think there should be, because I remember there are some research talking about it, but that's not being tested in our case. But the thing is, we can detect the openness pretty accurate. If there are really differences exist, we should be able to detect them and do a classification of the...
Yeah, the reason I'm asking is I'm wondering whether there's observed differences in the openness data.
Yeah. We thought about it, but it was a bit hard to collect the data set.
Right, yeah. Thank you.
Yeah.
Thank you, Dongyin again for